By definition, the rectilinear motion of a particle occurs along a straight line. All quantities like displacement, velocity, acceleration are directed along the straight line, and therefore they can be analyzed as scalars with either positive or negative sign, indicating the only two possible directions. However, when we enter into planar or two-dimensional motion, things would become very complicated. Fortunately, we can still break the problem into components, analyze these simpler problems separately, and then superpose their solutions to get the overall result. This principle of superposition of motion is demonstrated dramatically in a thought experiment called the monkey shoe. Let us consider a less violent version of this experiment over here. So suppose we have an apple tree over here where we have a very ripe apple about to drop on its own, and then someone on the ground is hurling a stone directed exactly at the apple. So the person is not making any correction for the fall due to gravity. Coincidentally, the very moment this stone leaves the ground, the apple gets detached from the tree and starts its free fall. The question is, would the stone hit the apple? If at all it happens, it will be somewhere in midair. So this looks like an extremely complex interaction. So to simplify this, let us take gravity out of this scenario. So we have opened this animation parameter dialog where we can control the velocity of the stone and the gravitational acceleration g. Let us edit it and make it 0. So there is no gravity. In that case, the stone will just go along this straight line, and the apple, though it gets detached from the tree, will not drop down. And the result is pretty obvious, though we can see it in the animation, that the stone is going to hit the apple, which is now hovering in the air. Let us try this experiment with gravity now. So I will edit this back to 9.8 meters per second and launch the stone again. This time it's drooping down and the apple is accelerating down, and the two actually meet at this point. So the stone hits the apple. But was it some lucky coincidence? Was it some special velocity that did it? Let's check. So we will change the velocity this time. We will launch the stone faster. Say instead of 32, let's make it 35 and try this again. This time the stone will rise higher, of course, but the result is the same. It still hits the apple. In fact, we can keep trying different velocities. Say instead of 35, we could even try say 38 or something and still get the same result there. Now, why does that happen and what does it mean? To understand that, let us go back to this zero gravity case where the stone went straight for the apple, hovering weightless in midair, and hit it. The only difference the stone's velocity would make is to hit the apple sooner or later, but it will hit it for sure. Now, introducing gravity, which acts equally on all bodies, would alter both the trajectories but through the same downward distance, and therefore they will still intersect at the same point of time and the stone will hit the apple, irrespective of its velocity and irrespective of the value of gravitational acceleration.